Self-organization is a process where some form of overall order or coordination arises out of the local interactions between smaller component parts of an initially disordered system. The process of self-organization can be spontaneous, and it is not necessarily controlled by any auxiliary agent outside of the system. It is often triggered by random fluctuations that are amplified by positive feedback. The resulting organization is wholly decentralized or distributed over all the components of the system. As such, the organization is typically robust and able to survive and even self-repair substantial damage or perturbations. Chaos theory discusses self-organization in terms of islands of predictability in a sea of chaotic unpredictability. Self-organization occurs in a variety of physical, chemical, biological, robotic, social, and cognitive systems. Examples of its realization can be found in crystallization, thermal convection of fluids, chemical oscillation, animal swarming, and neural networks. Overview. Self-organization is realized in the physics of non-equilibrium processes, and in chemical reactions, where it is often described as self-assembly. The concept of self-organization is central to the description of biological systems, from the subcellular to the ecosystem level. There are also cited examples of self-organizing behavior found in the literature of many other disciplines, both in the natural sciences and the social sciences such as economics or anthropology. Self-organization has also been observed in mathematical systems such as cellular automata. Sometimes the notion of self-organization is conflated with that of the related concept of emergence. Properly defined, however, there may be instances of self-organization without emergence and emergence without self-organization. Self-organization usually relies on three basic ingredients: strong dynamical nonlinearity, often though not necessarily involving positive and negative feedback; balance of exploitation and exploration; multiple interactions. Principles of self-organization. The original principle of self-organization was formulated in 1947 by the cybernetician William Ross Ashby. It states that any deterministic dynamic system will automatically evolve towards a state of equilibrium that can be described in terms of an attractor in a basin of surrounding states. Once there, the further evolution of the system is constrained to remain in the attractor. This constraint on the system as a whole implies a form of mutual dependency or coordination between its constituent components or subsystems. In Ashby's terms, each subsystem has adapted to the environment formed by all other subsystems. The principle of order from noise was formulated by the cybernetician Heinz von Förster in 1960. It notes that self-organization is facilitated by random perturbations that let the system explore a variety of states in its state space. This increases the chance that the system would arrive into the basin of a strong or deep attractor, from which it would then quickly enter the attractor itself. A similar principle was formulated by the thermodynamicist Ilya Prigogine as order through fluctuations, or order out of chaos. It is applied in the method of simulated annealing that is used in problem solving and machine learning. History of the idea. The idea that the dynamics of a system can lead to an increase of the system's organization has a long history. One of the earliest statements of this idea was by the philosopher Descartes, in the fifth part of his Discourse on Method, where he presents it hypothetically. Descartes further elaborated on the idea at great length in his unpublished work The World. The ancient atomists believed that a designing intelligence is unnecessary to affect natural order, arguing that given enough time and space and matter, organization is ultimately inevitable, although there is no preferred tendency for this to happen. What Descartes introduced was the idea that the ordinary laws of nature tend to produce organization. The economic concept of the invisible hand, due to Adam Smith, can be understood as an attempt to describe the influence of the market as a spontaneous order on people's actions. Beginning with the 18th century, Natural scientists sought to understand the universal laws of form, in order to explain the observed forms of living organisms. Because of its association with Lamarckism, their ideas fell into disrepute until the early 20th century, when pioneers such as Darcy Wentworth Thompson revived them. The modern understanding is that there are indeed universal laws, arising from fundamental physics and chemistry, that govern growth and form in biological systems. Sadi Carnot and Rudolf Clausius discovered the second law of thermodynamics in the 19th century. It states that total entropy, sometimes understood as disorder, will always increase over time in an isolated system. This means that a system cannot spontaneously increase its order, without an external relationship that decreases order elsewhere in the system. Originally, the term self-organizing was used by Immanuel Kant in his Critique of Judgment, where he argued that teleology is a meaningful concept only if there exists such an entity whose parts or organs are simultaneously ends and means. Such a system of organs must be able to behave as if it has a mind of its own, that is, it is capable of governing itself. The term self-organizing was introduced to contemporary science in 1947 by the psychiatrist and engineer W. Ross Ashby. It was taken up by the cyberneticians Heinz von Förster, Gordon Pask, Stafford Beer, and von Förster organized a conference on the principles of self-organization at the University of Illinois Allerton Park in June 1960, which led to a series of conferences on self-organizing systems. Norbert Wiener also took up the idea in the second edition of his Cybernetics, or Control and Communication in the Animal and the Machine. Self-organization as a word and concept was used by those associated with general systems theory in the 1960s, but did not become commonplace in the scientific literature until its adoption by physicists and researchers in the field of complex systems in the 1970s and 1980s. After Ilya Prigogin's 1977 Nobel Prize, the thermodynamic concept of self-organization received some attention of the public, and scientific researchers started to migrate from the cybernetic view to the thermodynamic view. Developing views are the views of self-organization in physical systems interpreted as a strictly accumulative construction process, commonly displaying an S-curve history of development. As discussed somewhat differently by different researchers, local complex systems for exploiting energy gradients evolved from seeds of organization, through a succession of natural starting and ending phases for inverting their directions of development. The accumulation of working processes which their exploratory parts construct as they exploit their gradient becomes the learning, organization, or design of the system as a physical artifact, such for an ecology or economy. For example, Begin's books and papers describe his approaches. Constructor Theory. P.F. Henshaw's work on decoding net energy system construction processes termed natural systems theory uses various analytical methods to quantify and map them, such as system energy assessment for taking true quantitative measures of whole complex energy-using systems, and for anticipating their successions, such as models learning change to permit adapting models to their emerging inverted designs. G.Y. Georgiev's work is utilizing the principle of least action in physics to define organization of a complex system as the state of the constraints determining the total action of the elements in a system. Organization is then defined numerically as the reciprocal of the average action per one element and one edge crossing. If the system is described as a network, the elementary quantum of action, Planck's constant, is used to make the measure dimensionless and to define it as inversely proportional to the number of quanta of action expended by the elements for one edge crossing. The mechanism of self-organization is the interaction between the elements and the constraints, which leads to constraint minimization. This is consistent with the Gauss principle of least constraint. More elements minimize the constraints faster, another aspect of the mechanism, which is through quantity accumulation. As a result, the paths of the elements are straightened, which is consistent with Hertz's principle of least curvature. The state of a system with least average sum of actions of its elements is defined as its attractor. In open systems, where there is constant inflow and outflow of energy and elements, this final state is never reached, but the system always tends toward it. This method can help describe, quantify, manage, design and predict future behavior of complex systems. To achieve the highest rates of self-organization to improve their quality, which is the numerical value of their organization. It can be applied to complex systems in physics, chemistry, biology, ecology, economics, cities, network theory and others, where they are present.